Thank you. I'm Kelby, and I'll be talking about new classes of vulnerabilities affecting single sign-on systems. These vulnerabilities were discovered relatively recently and are generally applicable to multiple systems. And in some cases, these vulnerabilities enable authentication bypasses and allow attackers to pivot from one user account to other user accounts. So a quick note about myself before I dive into the research. My professional and research interests are in cryptography, mathematics, and security engineering. If you like those things, feel free to check out my blog or Twitter, which are both listed here on this slide. And at Duo, most of my time is spent as a security advisor for product and engineering teams, as well as doing things like code and system design audits. And in fact, the research I'm presenting today was actually originally identified during an internal audit. So the goal today for this talk is to describe new classes of attacks on SAML and SSO and how an attacker could exploit them. At first, I'll discuss SAML at a higher level, so we're all roughly on the same page for the mechanisms that enable this vulnerability. And then from there, I'll dig more into the nuance of exploitation as well as mitigation. So with that being said, let's get started with SAML and SSO. There's quite a bit of ground I could cover here. SSO and SAML is pretty broad, but I'll cover just enough so the vulnerabilities seem intuitive. So SSO is really just describing a user experience where you authenticate to one service in order to access multiple services. In an ideal SSO world, users would benefit from this user experience because they would only need to remember one really good password in order to access multiple web applications. In a generalized SSO setup, there are three main characters. The first is your identity provider, which is often abbreviated IDP. The IDP is who you authenticate to in order to get access to these services. So for example, your organization's users directory. The second character is the user agent, which is really just a fancy term for a process acting on the user's behalf. And then for this talk, this is pretty much always just going to be a web browser. And then finally, we have a service provider, which is often abbreviated SP. And the service provider is just the service the user wants to access. This could be a payroll web application or some sort of chat service. One fairly common SSO flow starts with authentication to the IDP. The IDP then generates and signs a message intended for the SP, but passes it through the browser as some message passer. The browser takes this message and does its duty and passes it to the SP. And then when the SP receives this message, it then validates it and determines how to authenticate the user, if at all. So what's notable about this workflow is the fact that the browser process is under user control, and these messages that contain authentication information pass through it. So a service provider receiving these messages must be able to authenticate the contents of that message. And this is part of the problem that SAML and some of the related standards to SAML are attempting to solve. So SAML is the security assertion markup language and is a common standard used for SSO. There are other possible standards you could use to build an SSO system, like for example OpenID Connect. But from my experience, you'll see SAML more in a organizational context, whereas you may see OpenID or similar protocols in a consumer-facing context. And what SAML defines really is considering your IDP and your SP may be written by completely different entities and completely different teams. It's a common language that's shared across these different systems. And SAML also defines how other standards interact with it, such as those that provide message authenticity. So I think everyone in here would hate me if I put up a real SAML document, so this is a much more simplified example. SAML documents are just XML, and XML can get pretty hairy, so I removed a lot of that fluff. I would, however, like to highlight a few key elements that are in this XML that are the SAML messages that is used during SAML-based SSO. And the first is the subject and the name ID elements. So a subject element conveys information about the authenticating user. The name ID is just one part of the subject element and is defined as a string value that uniquely identifies the user. This could really be any identifier, but more commonly you may see things like email addresses or usernames. Service providers very often end up using the name ID to identify what user they want to authenticate to their service. The next interesting set of attributes are the attribute statements and attributes. So an attributes statement is just a set of attributes, and attributes are just very general properties about a user that the identity provider may want to convey to the service provider. So for example, an identity provider may use a user-selected username for name IDs, but still wants to inform the service provider of the user's email for notification reasons. This can also be used, as I've done in this slide, to convey information about a user's access control roles. And then finally, we need a signature to prove this information wasn't changed by this malicious user agent. And this is where the signature element and the XML digital signature standard comes into play, or XML DSIG. So SAML uses XML DSIG to sign documents and prevent this potential tampering by malicious user agents. And what this simplified signature element in this slide is conveying is that these signatures are included within the SAML messages that are passed within the different systems. And at first glance, that may seem like somewhat of a chicken and egg problem. How do you sign a document that contains its own signature? But that's really what XML digital signature, the standard itself, is specifying. Thankfully, most of XML DSIG is irrelevant for this presentation, but there's one key step of creating XML digital signatures that enable this authentication bypass, so I'll have to dig into it just a little bit more. And this step is XML canonicalization. So as you may know, digital signatures generally will become invalid if even one single bit changes in the signed text. And because signed XML documents may pass through multiple services and experience inconsequential changes like maybe formatting changes, XML documents are not signed as is. XML documents are instead signed in their canonical format. And canonicalization, which is a mouthful, so it's often abbreviated C14N, is a standard series of transformations that are applied to documents before these signature operations. And this prevents minor differences in signed documents from causing signatures to become invalid. Really, the key point here is that so long as the documents have the same logical meaning, they will have the same signature. And a demonstration of C14N can be seen in these three XML documents I've included in the slide. The first two are quite similar, aside from their attribute ordering being reversed. These two documents would have the same canonical form and therefore, despite having slightly different byte representations, would have the same XML signature. The last two documents are actually quite similar, except for the comment included in the last document. The last two documents could have the same canonical form, but it depends on the canonicalization algorithm that's used. Which, because we're dealing with XML, the fact that there are multiple C14N algorithms may not be surprising. However, for this talk, there's really only one distinction worth noting across these different C14N algorithms, and it's that some C14N algorithms remove comments prior to signature operations. That is, XML comments like the ones I included in the previous slide do not affect the signature at all. There are algorithms that do include comments as the canonical document. However, from my research, I think support of those of C14N with comments is not as frequently used, which I have to believe is due to this quote from the XML C14N spec, which suggests that implementations of C14N including comments is more of just of a recommended algorithm, whereas C14N without comments is a requirement. So given that I'm alluding to all this complexity of SAML and the complexity of the supporting specifications like XML C14N and the XML digital signature standard, if you were a developer wanting to implement a SAML service provider, you would be unlikely to start from scratch. And this is where SAML libraries and their APIs come in. So these SAML APIs are often abstracting a lot of these nasty details away to make the developer UX of implementing a SAML service provider really straightforward. On top of that, SAML is really just a language that conveys data. It's still up to the SP, the implementer of the SP, to decide what needs to be done with that data. And so we can see in this code snippet here how you could use the Python SAML API to build a very simple SAML SP. In this code snippet, the HTTP request object is processed and transformed into a SAML document object. This SAML object is then further processed and checked for things like signature validity. Assuming there were no errors during processing, we can extract the relevant data for our use case. And in our use case, we just need to extract the name ID element from the SAML XML. The username we extract is then used to authenticate our user. A subtle point here is that underneath the hood, these libraries do not often use the canonical XML for this post-processing step. So this means that the document used for signature verification may be slightly different than the document used for post-processing and all this data extraction steps that SPs need to do. To get a better sense of this, and considering that SAML SPs need to extract relevant SML or XML text during the authentication process, it helps to get a sense on how this is accomplished underneath the hood with these XML APIs. This code snippet is an example of what extracting a name ID may look like at the XML API level using the popular Python LXML library. So first we need to convert some string representing XML into an object, which we've done here. And then we can just call a simple .text method on that element to extract the inner text of the element. And then the output of this is just what you would expect, and it's the name ID value Kelby Ludwig. But one of the key findings of my research is how these APIs change when comments are added to inner text values. So given a comment has been inserted into the inner text, what would the output of this code be? One might expect it not to change at all, which is quite reasonable. However, the insertion of the comment actually ends up truncating the inner text. So you may ask, why did that value get truncated? It of course does depend on the implementation, but the probable answer here is that XML documents may be internally represented as trees by the underlying XML library because it's kind of a natural representation of XML. So in my first text extraction example, the document used could be seen as a tree with a single root and a single child node containing the full inner text. However, the second document may actually have 3 different child nodes. The first is a text node containing the first part of the text. The second would be a comment node. And then the third would be a node with the rest of the text. So if you view it in this manner, it may be a bit more clear about what false assumption was made. And it's that a root node may have multiple text nodes as children that represent a single string. So if it's assumed there's only one child containing the entire relevant text, a partial text extraction might occur. And although I haven't personally seen the case of this during my initial research, I've seen some systems that actually do things like extract strings from the last text node or extract comment text as well as part of that API. And what this really means is that there's a few possible variations of this attack, but for now we'll just assume that we're truncating text after the first comment. So is LXML broken? It's kind of hard to say. So other libraries do what LXML does in their methods for extracting inner text. Ruby's REXML, for example, will do the same thing and truncate inner text that has a comment in the middle. However, REXML documents this behavior, so it could be arguably viewed as correct. Maybe another perspective you may take on correctness is whether a language ecosystem is consistent. Other Python libraries like Python's XML tree has a .text method that would ignore the comment and return a full inner text. This is not what LXML does, despite the APIs being very similar. So at best, you could probably argue that this behavior is technically correct, but technical correctness may not be intuitive, and unintuitiveness may be harmful. Take Python's mini-DOM, for example, which is a standard library XML API. That library doesn't provide a method for extracting inner text from XML nodes. They just give you a tree parsing API that allows you to write your own text extraction methods, which means you're involving the parsing and traversing of an XML tree to extract inner text, which means you could ad hoc recreate this truncation issue. So at this point, we know just enough about SAML and some of the underlying software to construct one of the vulnerability classes that I identified during my research. So to recap what we know so far, first, SAML documents are passed through an untrustworthy browser to convey authentication information within XML. These XML documents are signed to prevent tampering, but XML canonicalization algorithms often don't factor in comments into signature validity. And then on top of that, the XML APIs provided to SAML implementers may truncate text when a comment is added to the inner text. So our attack is simply taking a section of an XML document that looks like this and inserting a comment into the appropriate location. So the net result is that when this is processed by a vulnerable SAML SP, the comment won't invalidate the signature on that document, but would cause the subject's user identifier to become truncated. So in this example, authenticating as the user admin@victim.com.evil.com would allow an attacker to truncate their name ID to a different user, admin@victim.com. So in other words, the comment acts very similar to a lot of null byte attacks. So it gives me the capability to truncate my own credentials in order to become other users. So as I mentioned before, I first identified this vulnerability during an internal audit of a proposed dependency. And once I identified a single instance of this vulnerability, a root cause analysis suggested it could be more widespread. Testing that hypothesis turned out to be actually quite efficient. So with the help of a couple of other Duo researchers, we hunted down other open source SAML implementations to try to identify similar faulty behavior. And our main strategy for doing this was really just weaponizing existing unit tests. So to explain what I mean by that, many open source SAML libraries often included a set of unit tests where at least one of them involved extracting a value like a name ID from a canned signed SAML document. So to identify if a library was vulnerable, we merely needed to take a test that was in that format, add a comment to, and ensure the test still passed. This allowed us to quickly identify multiple open source projects that were affected by this vulnerability. So the initial research identified 4 open source libraries that were affected: Python SAML, Ruby SAML, SAML2JS, and Omniauth SAML. The last project was actually built using Ruby SAML, so the presence of the vulnerability had propagated into a completely different project. And then throughout our disclosure process, there had been additional projects that self-reported being vulnerable, such as Shibboleth's OpenSAML C++. So an interesting aspect of this research is that these are known vulnerable SAML libraries or dependencies. So this means that the scope is likely larger than just these 5 projects, because service providers or products reliant on vulnerable versions of these libraries are likely affected. And this also doesn't account for any one-off SAML implementations that may have recreated this vulnerability themselves. And this is the subset of products that I'm aware of that have been affected by the comment truncation vulnerability. This includes products such as Shibboleth's SP, GitLab, a few Symantec products, and the product I alluded to earlier where this was originally found, the Duo Network Gateway. A good chunk of these products had SAML implementations based on libraries that I previously mentioned. And it's also worth noting that these products are mostly on-premise, meaning the users are responsible for the installation and update process. There could be SaaS services that were affected because SaaS services also deploy SAML SPs, but SaaS services don't always publish release notes when they patch a vulnerability on their backend, so those cases are a bit harder to track. And finally, this is the timeline of our findings and research. So as I mentioned before, I identified the first issue during an internal audit last December. 3 days after that, while simultaneously sorting out what a good patch would look like for a seemingly new vulnerability, we had identified 3 other vendors that were affected. And since we were dealing with multiple affected vendors, we opted to work with the CertCC group to coordinate disclosure across these vendors, as well as other common SAML IDPs and SPs. And then coordinated public disclosure was done around 2 months after the initial contact to CertCC. So switching gears a bit, let's take some time to look at how this vulnerability could be exploited. So given that we know we can find a vulnerable SAML service provider that allows us to truncate signed data, how could this be leveraged by an attacker? Does exploitation just require sheer luck to get an identifier that truncates to some other target? The answer to this is actually a bit more complicated. Both SPs and IDPs are fairly configurable or built in different ways, so there's quite a bit of wiggle room for configuring things or building things in such a way where risk is negatively or positively affected. We can first focus and look at how a service provider may sway exploitability. So to be more specific, the threat model of this attack first requires authenticated access to the identity provider. So initial access may be achieved through some form of account takeover, like phishing, or could just be carried out by an employee looking to access a coworker's data. This initial foothold, when combined with the comment truncation vulnerability, can be used to pivot to different user accounts. So at first glance, as I mentioned a minute ago, this may seem impractical since we may be reliant on our foothold account, which may not be lead to anything interesting. However, this is where SP-specific features make things easier for the attacker. So the first is which is something I alluded to earlier, is how SAML is sometimes used to convey authorization information. So recall the SAML attribute statement is just this general set of properties that are relevant to the authenticating subject. So a SAML document may use the attribute statement to, for example, inform SPs of a user's role. This adds another possible avenue for impactful value truncation. If the attacker's foothold account doesn't have an interesting user identifier to truncate, they may be able to truncate group names into something impactful. This attack really just generally applies to any XML element as well. So in this example in the slide, a user could have a lesser privileged role, administration role, like one that's scoped to HR administration. But if the attacker then truncated that to just the more general powerful administrator's role, the SP may be enabling a privilege escalation vulnerability. Another SP-specific detail is how name IDs are processed. So the only requirement for user identifiers conveyed via name ID is that it uniquely identifies a specific user. Identifiers could be anything from user-selected usernames to just completely opaque random identifiers. Using random identifiers is probably unlikely to be truncatable to anything interesting, but things like numerical user identifiers, which could be auto-provisioned to users, could be very exploitable because numbers like 104 could be truncated to become 10 or 1. Other identifiers such as email addresses and usernames are a bit more dependent on how accounts are registered. And since account registration is more of a function of the identity provider, I'll discuss that a bit more when we get into the IDP exploitability part of this talk. And before I get into IDP exploitability, I'd first like to cover the remediation of the truncation vulnerability. Both identifying a vulnerable system and the remediation process of that system depends on your relationship with the service provider. So if you manage or administer service providers, your best two options are, one, just asking the service provider if they're vulnerable, or two, just spinning up a browser proxy and testing things yourself, of course with permission. If you or someone in your organization maybe has written a SAML service provider, I would recommend following the weaponized unit test strategy that I described earlier to identify if your library or implementation is vulnerable. This, of course, assumes someone wrote tests, which may be a completely absurd assumption. So there are other mitigation strategies as well, such as rejecting SAML documents that are non-canonical, or just rejecting any SAML document that contains a comment, because it does seem kind of unlikely. But the efficacy and practicality of both those strategies depend a bit on your context, so you would have to just test that first. So up until this point, I've heavily focused on exploiting the service provider, but the service provider is really only one part of the SSO equation. And even though service providers are usually the entity making the comment truncation mistake in an impactful way, in my opinion, most of the risk-increasing features actually are a product of the interplay between the identity provider and the service provider. So let's dig in a bit more into what features or configurations of an IDP may sway exploitability of this vulnerability. The first feature that could possibly reduce the impact of this vulnerability is two-factor authentication. However, whether 2FA really helps completely depends on what system or systems are enforcing 2FA. So if the IDP is responsible for enforcing 2FA, that may not provide much additional protection against a vulnerability dependent on your threat model. So since our threat model is based on a user with an authenticated session, an attacker already has authenticated access to the IDP. 2FA may increase the cost for the attacker to get that initial foothold, but 2FA doesn't really help in the case for a malicious insider who has the capability to provide their own second factor for their own account. And since SAML document tampering takes place after the IDP's authentication is complete, identity provider enforced 2FA doesn't actually meaningfully limit risk of exploitation. If the SP enforces 2FA or the SP enforces 2FA in addition to the IDP, exploitation opportunities of this vulnerability are a bit more limited. So that is, if the SP would likely extract the user identity from the SAML document in order to look up the user's 2FA information. So in this case, the comment truncation vulnerability would just cause the SP to look up the victim user's 2FA and would require a bypass of that user's 2FA as well in order to get access. So another variable that can greatly influence impact, as I mentioned previously, is how IDP users are registered. So self-registration is a pretty standard practice for consumer services, but from my experience, SAML-based authentication is less common in the consumer service space. Organizations, on the other hand, may manually provision all their employees, but identity providers do offer self-registration options that can be used to reduce IT burden. And an attacker who takes advantage of self-service user registration for an IDP would likely increase the impact of this vulnerability, as the attacker can just provision user accounts themselves, which may give them the opportunity to pick their own SSO identifier. So if I'm able to choose my username, I can just pick a username that matches my target plus some junk at the end, and then just truncate it later. So another potentially risky IDP feature is account lifecycle functionality, such as user profiles. So if an IDP also functions as an employee directory, employees may be able to do self-service profile management, such as updating their first name or phone number. In other words, if an identity provider allows a user to edit the data that they use for SSO identity, they may have some influence over how they're identified. And I'll use the term mutable identity to describe user profiles that exhibit this behavior. In fact, I think mutable identities are an interesting enough concept that they're worth digging into a bit more. And that is because mutable identities are interesting because users are able to influence their SSO identity. And this really increases the impact of comment truncation vulnerabilities. So just like user registration may allow an attacker to choose their own identity so they can truncate it however they please, mutable identities allow users to update their own identity to be conveniently truncatable. So to get a better sense of this concept, we can see an example of mutable identity in LastPass Enterprise's SSO feature. So similar to other identity providers, LastPass is an enterprise feature that gives users a launcher view for all the service providers that they have access to. So if an administrator has configured a user's email identifier for their account as a SAML name ID for one of these service providers, the name ID would end up updating after the end user updated their email information. So this allows a user to update their SSO name ID to any email address they can prove ownership of. This in normal circumstances actually is not much of an issue because an attacker wouldn't likely be able to prove ownership of a victim's email address. However, when combined with the comment truncation vulnerability, it becomes trivial to use this mutable identity property to target any user. So this is what an example exploit of combining both the comment truncation vulnerability and mutable identities would look like. So in this case, I'm acting as myself, an employee within Duo, looking to target our CTO, Jono. I first need to find a SP that's vulnerable to comment truncation and also uses email addresses for identity. So this can really just be detected by authenticating to services that I have access to, inserting comments into the SAML assertions, and then observing responses from the SP. If I get like an error response or maybe some form of default user access, that's a good indication that the service is vulnerable. So once a vulnerable SP is found, I can update my LastPass account email under a domain I own. So for example, pretending I own attacker.com, I could just use the email address jono@duo.com.attacker.com. Since I own attacker.com, this is an email I can prove ownership of and follow through in LastPass's confirmation email. And once the email is confirmed and my LastPass profile is updated, so is my name ID used for SAML SSO. From there, I can re-authenticate to the vulnerable SP, insert a comment before the part of my domain, so .attacker.com, and authenticate as my target user. I've actually recorded a demo of this exploit workflow using LastPass Enterprise SSO, as well as a demo SAML service provider that is vulnerable to the comment truncation vulnerability. So this first video actually just demonstrates the LastPass SSO workflow, as well as my demo vulnerable SAML service provider, which just really logs to the UI who I've authenticated as. So you'll see I start the attack with a standard organizational email like my name @duo.com. And then once I authenticate using the LastPass SSO, my LastPass name ID is just shown in the UI there. So just normal authentication process, nothing fancy. This video demonstrates the LastPass email update functionality, which is mutable by end users. So here I'm updating that previously used email address that was in the organization, my name @duo.com, to target the email address of Duo CTO under a domain I own, which is jono@duo.com.kel.bz, because I actually don't own attacker.com. I can confirm this email since I do own this domain, but I do that out of BAM because reading my email on a video is boring. And then finally, after proving ownership of that email address, which I did out of ban, my LastPass account email was updated. And what this video demonstrates is my ability to authenticate as a different user in the organization using the comment truncation vulnerability. And what you'll note is at one point I enable a browser extension in the top right corner of my browser. And really what that is just a browser HTTP proxy that inserts comments into SAML messages passed through my browser. So this video starts off with me killing my last session with the service provider, and then I re-authenticate to the demo service provider again. And what this first authentication does is just demonstrates that my email address has since been updated to the one that I did out of ban. So after enabling the browser proxy, which I just did, and killing my session, I can log in again, which inserts the comment in the appropriate location, and now I've logged in as an arbitrary duo.com user. Thank you. So to wrap things up, so I hope this talk demonstrates that even old and frequently used systems still have some interesting vulnerability classes lying dormant underneath piles and piles of complexity. And then I'd also like to emphasize that we could only look at so many systems, and I hope this talk inspires a few of y'all to go out and look at your own SSO setup and see what you can find. And then finally, I'd like to give a shout out to CertCC and Duo for supporting this research, as well as the coordinated disclosure, and as well as a big thanks to any vendors who provided patches for their users. And with that, thank you all as well for coming.